the most common use of machine learning in information retrieval is for classifying texts. So suppose you've got a collection of pieces of texts, maybe Twitter, maybe Newswire, something like that, and you're trying to predict something for each piece of text. So examples of that could be you are filtering an email stream for your email user, and you're trying to figure out if each email is spam or non-spam. Or maybe you're trying to detect censorship on the web. So you've got a social stream where you suspect some censorship is going to happen, and you want to predict whether a tweet or a post will be censored before it actually does. So maybe you're doing sentiment analysis, so you're analyzing blogs, you're working for a particular company, and you want to automatically figure out the guy who posted this blog, does he love us or does he hate us? Is he saying positive or negative things about our product? Or maybe you just want to predict stock prices based on news stories that come out every day. So there's lots and lots of applications of text classification. And in all cases, what it boils down to is you have some set of training examples. So you have some texts that are positive for some class, some texts that are negative. So you're going to represent them in some space. So then a new document D is going to come along, and your goal is to predict whether D is more likely to be positive or negative, given the training examples that you've had. So that's the classical classification problem. And believe it or not, even though we haven't talked about machine learning, we've already covered one algorithm, one very simple algorithm that you could use to perform text classification. Remember when we talked about relevance feedback? Right? Relevance feedback, user gives you some examples of relevant things, some examples of non-relevant things, and your goal is to re-rank the documents in that case. But you could use the same exact algorithm, very simple idea, for classifying documents. So a Centroid classifier or a Rocchio classifier, that would be the implementation of that idea. And what it would do is, it would basically say, okay, everything is a vector of words, all our training examples are vectors of the vocabulary, document D is a vector of the vocabulary. What we're going to do is, we're given some positives, some negatives, we're going to compute an average positive and an average negative document. So a centroid of all the positive examples and a centroid of all the negative examples, right? So maybe that's a negative centroid C minus and that's a positive centroid C plus. And then the Rocchio algorithm tells us how to rank documents with respect to these centroids. This time we're not interested in ranking, we're just interested in saying yes or no. Is a new document positive or negative? So what you could do quite simply is to, for any new document that comes in, you compare it to the positive centroid, compare it to the negative centroid, and see which one is it closer to. Right. So in this case, document D is closer to C+, so you would classify it as a positive class. Right. Really, really simple rule. Takes no cleverness to implement. Now let's look at what this solution actually looks like in space. Right. So what I'm interested in is, what is the decision boundary? So this particular document, yeah, it's closer to the positive, right? So what is the boundary that would separate the positives from the negatives in this case? And the boundary is actually quite simple. It's just the set of all points that are closer to C plus than closer to C minus. So one way I could represent that is by saying, well, if I use a dot product to measure similarities between a centroid and a document, then I want a higher similarity or a higher dot product for the positive centroid than for the negative centroid. And if you try to plot a decision boundary that corresponds to that, it'll just be a vertical line in this case, right? So all the points to the right of the line are closer to C+, all the points to the left are closer to the C minus. So everything here you would classify as positive, everything on the left you would classify as negative. All trivial, all totally obvious. Great. So that decision boundary, it's just the difference of the two dot products. Now you look at this and you'll notice that the D in both parts is the same. So let's take the C plus and C minus and put them together so that we have just one dot product. So you could write the same exact thing like that, right? if some vector W was just the difference between the positive and the negative centroids, then you're taking this vector W, doing dot product with D, with the document D, and seeing if that is positive or negative. So that's just equivalent. That defines the same thing. Now, what does this vector W look like? Well, you should already know what it looks like, but if you don't, the analogy is very simple, right? Everything is a vector in this space. C minus is a vector, C plus is a vector, and W is just the difference between C plus and C minus. So it's a vector that points from C minus to C plus. And it's going to be a vector that's perpendicular to the decision boundary. It's a normal vector, right? So for every decision boundary, there's a normal vector, W. Great. So what we've done is we've taken our very simple centroid classifier and we've turned it into a simple rule where we're saying that the decision boundary, yes, it's defined by C plus and C minus, but really C plus and C minus define a weight vector W, and that weight vector is going to define a linear decision boundary in our space.